John, Stanley, K4ERO, you are on. You should have control for your slides.
Okay, real good. And I'm very happy to see how many folks were willing to come and hear me as opposed to going to a swap meet. That's a that's a real compliment. So good to see all you guys. And I do want to start by sharing this screen here, and I hope that will come up. Looks like it's there. Okay. So we'll call this program Antipodal Focusing, Working the Ultimate DX. And this is based on an article in the March 2025 QST, which Bob read and decided it was worth hearing more about. And I have listed some of the call signs that I've operated under through my career. I have been DX more than I have worked DX. And in fact, as you look at those call signs there, some of them possibly might ring a bell, particularly the HC1JX, which I operated for 13 years, S79J for about a year, and some of those others. And so if I've worked any of you guys using any of those call signs, I'm happy to provide a verbal confirmation if you will let me know. I'm presently, have been for a long time, an ARRL technical advisor. I'm presently one of the QST technical editors, but my career was in shortwave broadcasting, which is what took me to all of these exotic locations. Some not quite so exotic, but interesting. I also learned a little bit more about the ionosphere when I was working as a consultant with the High Pass Ionospheric Laboratory in Fairbanks, Alaska, which was a project of the UCLA Plasma Physics Department. So I want to start off with a brief introduction to shortwave propagation. I think most of you guys could probably tell me some things about that. But for those who might be a little bit new to it, I want to just give a brief introduction. Then we'll talk about what is antipodal focusing and help everyone to figure out where your signals focus using this phenomenon. And if we have time, some questions and answers. So with that, I'm going to change screens and I'm going to go to a program that I hope all of you are familiar with. If you're not, you should be, although this is only one of a number of, now why didn't that work? I tried to switch over to another program. Let me try stopping sharing and start again and see if it will come up. That worked. Okay. So let me make that go full screen. It looks like it is full screen already. Okay, that's good. So this is the famous VOA cap uh, propagation prediction program. I don't know how many of you use this. There are other programs that may be better for ham purposes, but I just want to illustrate a few things using this program. And at the same time mention its limitations. This program, as you might guess, was written by the Voice of America people. And as such, it is optimized for shortwave broadcasting purposes, not for ham radio, but there is a ham radio version. And this is online, by the way, and you don't have to download anything. You can just go online and use it. And even though it's not perfect for ham radio purposes, it is useful. I have programmed into this at the moment here a path which goes from Santiago, just south of Santiago, Chile, which is where I did my CE3 operation from, portable CE3. And I think I have put the other end of the path very close to where you guys are. But you can tell me, I'll zoom in. No, I've got it a little bit too far north. Uh, is that about right? Where are you guys located mainly?
Going to be east of Sacramento. East of Sacramento.
East. Okay, maybe there.
Yeah, that's getting close. That's good
Okay.
enough.
Okay. So having defined a path that is between where I operated from in Chile and where you guys are now. And I don't remember if I worked any of you, but I might have. And when I was there, I was at a shortwave broadcasting station that was being refurbished. And because of that, the transmitters were offline, meaning that all of the antennas were available. And so I used a number of them, anywhere from 4x4 curtains, which means 16 dipoles in front of a reflector screen. Those were pointed at Europe. The antennas that were pointed at North America were 4x4 log periodics. In other words, two high, two wide log periodics that covered 6 to 26 megahertz and worked rather well on 40 meters. 17 dBi gain, which is quite a bit more than the average person would use on 40 meters. In fact, this worked so well that I used a 100-watt rig. And one evening when I went in, I accidentally, without realizing it, had set the rig to operate QRP with 10 watts. And I didn't notice for about a half an hour that I was working a lot of stations in the States with 10 watts on 40 meters. But I want to just show you what this program is good at, and I'll show you later some things that it's not so good at. Uh, we are looking at the results of the propagation using single sideband 100 watts, and we are beaming from Chile to your location. And over here on the chart, you will see that on the 40-meter band, we would be expected to have good signals between about 2 UT time and about 12 to 13 UT time. Well, really about 11 to 12. The best time being, of course, right in the middle of that period. Now, any of you who've worked any DX at all are well aware of why this is. We can move the terminator by moving this bar here on the bottom. And if I set this to about 2 UT time, you'll see that that's the point at which we begin to have an all dark path. And so naturally on 40 meters, we have strong signals. That all dark path continues until the sun rises in Chile, which occurs at about 1100. And you'll see up here on the chart, 1100 is about the time when signals start to drop off. So this is an illustration of the way this program works. It's very easy to use, really. You just drag these various points to the place of interest. You hit a button up here in the corner, which says prop charts or prop wheel. The wheel is a little different format, but gives the same information. And having done that, you will get this nice chart up here, which shows you what propagation to expect. The two curves that are plotted here, by the way, are the signal strength on an S meter and the reliability as a percentage. So I suspect that most of you are familiar with this software. If you're not, I would encourage you to investigate it unless you have something that's more suitable. So with that, let me go back to the other screen that I had. And apparently to do that, I need to stop sharing and then share again. So we will do that. So the next thing we want to talk about, this is what we just looked at, by the way. And here is here's the link if you want to use that program. But if you would just put in a search engine VOA cap, it would probably take you to a place where you can find this. But that's the exact site that I was using to do the demonstration that we were just talking about. By the way, this round thing here is the other type of display, what they call the prop wheel. And you can see on it that the red, which is the strongest signal, lies between 2 up here, 2 UT, and 10 UT or 11 UT. And that tells you that's when the 40-meter band is open on that particular path. So having looked at that, we'll come back to that program a little later. Let's go on to talk about antipodal focusing. So first question is, what is the antipode? You'll notice the pronunciation here is different. When it's just the singular, it's the antipode, which is the point on the exact opposite side of the globe from where you are located. What are the antipodes? Again, we look at the pronunciation, which is now different. Antipodes is the area that is close to the antipode. And in common, at least British English speech, it's used to refer to Australia and New Zealand, which are located approximately at the antipodes relative to the United Kingdom. And what is antipodal? That's an adjective that relates its noun to effects that occur in the antipodes. Every point on Earth has an antipode and an area called its antipodes. And by the way, if you mispronounce these words, I won't get upset at all. I probably will do so myself so sometime during this presentation because they are a little bit illogical and goofy. But that apparently is the correct pronunciation for these words. Now, the question is, if we're going to talk about antipodal focusing, we have to think about what focusing is. Most of us have an intuitive grasp of that, but just a quick review. Focusing means concentrating energy into a small area, and it is the opposite of dispersion. So if energy is emitted from a point source, it spreads out in three dimensions, and this means the energy decreases as the square of the distance. This is what we normally use to determine how fast our signals decrease as they go away from our antenna. And this certainly would apply, for example, with UHF antennas in what we would call direct paths, or sometimes called ground wave, but it's really direct paths. Certainly from in space, that's the way energy spreads. Now, if we confine energy to two dimensions, it makes it decrease directly as the distance rather than the distance squared. This happens between the Earth and the ionosphere and with water waves in a pond. Ripples in a pond are only spreading in two dimensions. And in the same way, energy trapped between the Earth's surface and the ionosphere, once they have reached the height of the ionosphere, they are spreading in three dimensions up to that point. But once they reach the ionosphere and are reflected back, then they only spread in two dimensions. And so they drop off, the signal drops off, neglecting other losses, which is very important. But the distance loss is only directly as the distance, not as the square of the distance. Just as an interesting point, if we confine energy to only one dimension, it means it doesn't decrease at all, except for losses, resistive losses. That, for example, happens in a waveguide. If we put a signal through a waveguide, it comes out the other end almost 100%. We know there are slight losses, just as there are in a coax, but typically in a good piece of waveguide that's the right size for the waves that are in it, it will drop off very, very little. Now, either reflection or refraction can focus energy if done properly. We know that in a mirror, if energy is coming from this red spot here and hitting a concave mirror, if the mirror is properly designed, the energy will converge at another point. So it's focused by reflection. Also, we know that we can focus energy or light, particularly with refraction. That's what happens inside of a lens. So the question I have for you is, does the ionosphere reflect or refract radio waves? Would anybody care to offer an opinion on that subject?
Well, people generally say reflect, but I think it's more of a refraction thing. But mostly it's a guess.
Yeah, that's really the correct answer. Let me expound on that a little bit. If I can move my pictures out of the way here so I can get to here. Uh, the ionosphere is a plasma, and strictly speaking, if a wave enters a plasma, it is refracted. That is, it is bent. And you see this wave coming up here. This would represent a wave that is above the MUF. So it will be refracted or bent while it's in the plasma. But as it begins to exit the plasma, it will be bent back in the other direction. Now, the reason for that is that the plasma is thickest in the center and thinnest at the edges. As you go from a thinner to a thicker plasma, you bend away from the heavier, the thicker part. So the wave would bend in this way and then pass on through if it's above the MUF. If it's below the MUF, before it reaches the point of highest ionization, it will become horizontal and then begin to bend furthermore as it goes back out of the ionization. And if this ionization is reasonably smooth, that is thinner, then thicker, then thinner at the top, it will come out at an angle that is very similar to the angle at which it entered. You'll remember from reflection the old rule that the angle of incidence is equal to the angle of departure. And so it very much resembles a wave that has been reflected from the ionosphere. And so you'll find in the literature that it's very common to refer to reflections from the ionosphere, even though if we wanted to get real technical, we could say that that's actually refraction in the ionosphere, but the net result is very much like a reflection. Okay, so how does antipodal focusing occur? And in the article, I used this illustration. Consider this to be the North Pole at the top and consider it to be the South Pole, obviously at the bottom. And this represents a pulse, let's say 1 dit of CW, rather fast CW, being sent from a transmitter. And you'll see that it's making its way around the world. Now, as it spreads up here, it starts spreading as an inverse distance. With inverse distance, this energy is decreasing, and that continues. But as it approaches the equator, it reaches a point where it is no longer spreading. In fact, it begins at that point, the energy begins to pull together or to shrink instead of spreading. And because it does that, it begins to strengthen, actually, neglecting again losses that we'll talk about, but it begins to pull together. And by the time that pulse reaches the South Pole, if this were an absolutely smooth and lossless ionosphere and Earth's surface, all of that energy that we put into the ionosphere at the North Pole would show up at a very small point on the South Pole. Now, again, that's theoretical based on some unrealistic assumptions, like no loss, no delayer, no, no nothing, but just a smooth, perfectly reflecting ground and ionosphere. Nevertheless, there is a focusing effect that does occur. Now, if again in the perfect case, it would come to a point, a small point. But if it's in the real world, it does not come to a point, but is rather smeared out, just like an imperfect lens will not focus a point source perfectly. In the same way, the imperfect ionosphere Earth combination will smear out the focusing effect. So we have places where either the ground is rough, mountains and so forth, or the ionosphere is rough. The ionosphere is not perfectly smooth on its underside. It has undulations and variations due to various things. If it were smooth, we would have this perfect reflection, but we don't. We have some scattering. In addition to that, on the daytime side of the Earth, we have this blue line, which represents the D layer, which absorbs some of the energy. We also have an F layer represented by the green line, which is lower, and that has its effect. On the nighttime side, the D layer fades away shortly after sunset, but we have an E layer that persists. It eventually fades away as we get further into the darkness. At least it gets less. It never fades away completely, but it gets less. And that layer is higher than the F layer during the daytime. So that means that the reflection takes place at a greater height, which means that each hop is longer. So the differences between day and night are quite dramatic in terms of the way our waves propagate, the speed at which they propagate, the amount at which they deviate from straight lines, and so forth. Then the other factor is, of course, that part of our globe, as we know, is covered with water, seawater, very good conductor, and part of it is covered by land, which might be a halfway decent reflector for radio waves, or it might be a horrible reflector for radio waves with various degrees of roughness and so forth. So, generally speaking, paths that go over seawater are better behaved than those that go over land. So, what is the difference between day and night paths? Absorption, the D layer is there in the daytime and goes away at night. The layer height is greater in the daytime, and the maximum density of the F layer is greater in the daytime. So all of these things work together to smear that point where the reflection might concentrate here at the South Pole in this case, if it were not for these other factors. But because of those factors, this area, which we would call the antipodal focusing area, is not just a point, but it's an area of at least hundreds of miles, if not possibly some effects even out to 1,000 miles from that exact point. So we want to think a little bit about long path propagation as opposed to short path. There are certain paths that are famous for long path. I was in India for 3 years, and I used to keep a schedule on the 20-meter long path back into the eastern US. Very, very reliable. I think the long path to Australia is another one that people can count on pretty much. There are other times when the best way to get from one place to another is to go on the long path. Now, why might that be? It might be because the long path, even though it's longer, more than halfway around the world, is in nighttime if it's a low frequency, or it's in daytime if it's a high frequency. And it might be because that path, the long path, also is over water, whereas the short path might be over land. So, with that, let's go back to uh, well, we'll do this other stuff here first, and then go back, so we're not switching back and forth since it's a little bit complicated. A question that always arises when we're talking about long path or even reasonably long path propagation is, where should a person point their beam antenna? And so we have this famous thing, which it's called here. This is courtesy of NS6T, by the way, and I'll show you, if you're not already aware of it, where you can download these maps or generate these maps yourself online. Very, very useful site. So we're thankful to Tom NS6T for this map. Here is what I've always called a great circle map. He calls it azimuthal map. I don't know how to pronounce that word. But anyway, that's what he calls it. I call it a great circle map. And on this map, which this particular one is centered, by the way, on close to your location, it shows what direction you must point your antenna to get to any point on the globe. Now, this type of map cannot possibly show the antipodal point for the very simple reason that when we do this type of projection, the antipodal point becomes infinitely large. And so it makes it very difficult to plot it on a reasonably sized piece of paper. And so if you want to see what direction to point your antenna to get to the antipodes, you can't use this type of map. On this type of map, all of the lines that are straight lines going out from your location are correct indications of which direction you must beam in order to get to a particular point on Earth. For example, it might not be obvious at first glance that in order for a person in Northern California to beam to Europe, you have to beam at about 20 degrees In other words, quite to the north. Just looking at an ordinary map, you might think that I can beam due east, and I will get to Europe, but that's not true. If you beam east, you will end up out here in the middle of the Atlantic Ocean. If you beam at 20 degrees, you will end up in Europe. If you beam at 0 degrees, that is due north, you will end up over here in Turkey and some of those Middle Eastern, shall we say, countries. So it's very deceiving. Uh, on a globe, radio signals always travel in straight lines around the globe, except where the ionosphere has tilts. Now, when I say a straight line, of course, I mean a line following the surface of the Earth, but straight as far as we can be straight on the surface of a globe. So here's a few maps that I've drawn. Here's obviously the North Pole, and then here's the companion map from the South Pole. If we would paste these two together on two sides of a disk, you would see that they fit together. So in order to see the Antipodes from the North Pole, we can't do that by using this map. Again, it would make the South Pole infinitely large, but we can make a complementary map that is centered on the antipodal point. Now, I've done that for a few other places. My QTH is located at approximately 35 degrees and minus 85 degrees, 35 north, 85 west. And so the antipodes from me would be at minus 35, 105 degrees, and this is the plot of it. So if I want to know what the antipodal point is for me, I can look at this map and I will see that it's at a point that is fairly distant from the western edge of Australia in the Indian Ocean. Now, by the way, if you're going to do this for your location, there's a trick you have to be aware of. You take your latitude. First thing you should do is plot the Great Circle map for your location. Make sure it's correct. Then you reverse the sign of the latitude. You see, 35 goes to minus 35. But you don't reverse the sign on the longitude. If you did that, it wouldn't work. What you have to do with the longitude is you add 180 degrees to it if it is negative, which would be the case for anywhere in the US. And by doing that, you move the point east by one hemisphere. Or if you're in the eastern hemisphere, like in Europe or India, you subtract 80 if it's positive, and that moves it west one hemisphere. And that allows you to then calculate a map that will show exactly where the antipodes are for your location. So I did one for WWVH. I mentioned in the article that when I was in Africa, in the country of Zambia, I could hear WWVH because it was very close to the antipodal point, very strong. And so I did for WWVH, I did a map showing the antipodes, and indeed it does fall in the middle of South Africa. It's the southern part of Africa. Here's the place where you can do your own map if you want to take that down. ns6t.net/azimuth/azimuth.html, and it will take you to a site where you can plot your own maps based on the point that is the antipodal point from where you are, and that will help you to better understand exactly the point at which this focusing takes place. So I think I will go back now to VOA cap and look at some antipodal paths on VOA cap. So to do that, I've got to stop sharing. I've got to then share again. There may be a better way to do this, but this seems to work. Okay. Now let's verify a couple of things first. You remember that I said that if you wanted to beam to Europe from your QTH there in California, you have to beam what direction? You have to beam north, 20 degrees approximately. If you want to go to Turkey, you've got to be, this is a little bit actually east of Turkey. You've got to beam almost due north. That would be Iran. So that's very counterintuitive when you're using this type of a map, and that's why the Great Circle map is so useful. But here's what I want to show you, which is really quite interesting. What point on the globe is the antipodal point for you guys? And the way you find that on this map is you go down here and you find a point where this curve just goes crazy. The slightest little change in the direction of the curve, or in your location rather, changes drastically the direction of the curve. And that's the indication of the fact that you are very close to the antipodes for that particular location. Now, what do we have down here? Well, mainly a whole big bunch of nothing. Okay. But there is one very interesting thing, and that's this guy down here. So let's set our transmitter on that point. So one of you DXers tell me what this place is down there. Okay. What is that?
Oakland Islands.
Sorry? I didn't hear what you said. I'm sure some of you know what that is. It's a rare DX location. Is it heard? I'm not sure. Like I say, I've been DX more than I've worked DX. Anyway, looks like a good place for a expedition, right? So whoever's there, if they're transmitting, their antipodes is going to be this point right here, which is just up on the Canadian border in Montana. But as I mentioned, the antipodes for purpose of propagation is not a point, it's an area. And in fact, you down here, uh, what would that be, 3, 4, 500 miles away from the exact point, would still be getting some significant amount of focusing due to this phenomenon. Okay. So it's still a useful thing to know. Now, as I mentioned in the article, it's unfortunate that most areas with a lot of active hams are in places where for them the antipodes is out in the middle of nowhere. And so, with the exception of expeditions or things like that, most people aren't even aware of this phenomenon, except for our friends in Britain. And our friends in Britain are very aware of the fact that if we put our transmitter, or this happens to be the receiver, if I put our receiver over here close to England and go searching for the antipodal point for them, it will be right here, very close to New Zealand. Okay. And in fact, in response to my article, I got a letter from a ham in England saying that he had a buddy in New Zealand and they love to play around with that. And one of the things that they like to do is to change their antenna headings and see which way the path was working the best. Because as you can see, a very slight change in the location can move can change the path over which you're going by a very great deal. Now, I think my time is pretty much up. So with that, I think I'll see if any of you guys have any questions, and if not, we'll just leave it at that.
I have a question on the skew path, mostly on 10 meters. We find to Europe, we're pointing about 95 degrees, and then later we go to Europe. What causes that?
Okay, that is due to tilts in the ionosphere. And the ion, again, as I've said, the ionosphere is not a nice, smooth, perfectly smooth layer as we would like to think it is. And as, by the way, this particular program assumes that it is. That's not a very good assumption. There are frequently tilts in the ionosphere, and those often occur at the terminator. If your path is crossing the terminator, particularly crossing it at an angle like a 45-degree angle, the fact that the ionosphere is higher in the daylight and lower in the it's lower. Let me get this right. It's higher at night and lower in the daytime. Obviously means that the ionosphere is tilted. So if the ionosphere is tilted and you're crossing at an angle, it will bend your beam in as far as azimuth is concerned. Does that make sense?
Yeah, it does. Thank you.
Okay.
Question? Can you hear me?
Yes.
I noticed with a place like Beauvais that I could often hear them better 70 degrees off of short path. Long path didn't work at all, but my transmitted signal was received by them better short path than it was where I could hear them better. And the 70-degree shift is pretty significant. So my suggestion is that maybe the transmit path is not equal to the receive path consistently. Does that make sense?
It is not super common, but it certainly can happen that we have a non-reciprocal path. Some of that may have to do with the Earth's magnetic field, which splits up our beams into what we call an ordinary and an extraordinary ray. But this program assumes, and a lot of propagation programs assume that paths are always reciprocal. That is not a very good assumption.
It also ignores the polar cap. I live pretty far north. I'm about 800 miles north of near the Canadian border, where these guys are mostly in California. And when the KP is high, I don't even bother. It just because it
Yeah.
just quiets everything down to nothing.
Right. And you also get reflections off the aurora. I mean, the aurora is probably as good a conductor, maybe more so
Yes, what
than
do you
the
want?
ionosphere.
How are
It's
you?
still-
Huh?
How are you?
I'm okay.
So yeah, if you have an auroral path, that can do really
There's a
weird
start.
stuff.
Yeah, that's correct.
Yeah,
We're
Merv, you left your mic
in
on.
the garage.
Merv,
Yeah.
your mic is on. Yeah, it gets interesting up here this far north. It's that's the only word I can use that's polite.
Yeah. I spent quite a bit of time in Fairbanks, but unfortunately, while I was there, I did not operate. Obviously, could have done so without even applying for a license, but I just was doing other stuff.
Yeah, this is Whiskey 6 Whiskey Hotel Uniform. An ignorance question for you, John. What's the difference between 100 watts and somebody who's running a kilowatt? Is there any other than the obvious?
Well, I could show you this on this program, except that it seems to be somewhat locked up right now. Yeah, if you're running 100 watts and then you go to a kilowatt, you'll be 10 dB stronger. That's basically it. I mean, there's nothing about changing power that changes the path characteristic at all.
So would it
Except,
be fair to say that where you land on the other end is wider than 100 watts?
well, no, it's not. It's well, the point at which your signal is no longer listenable will be wider, just as it is on any path. Uh, you know, you could one of the things this program can do is it can plot coverage maps. And if you do that, that's very much used in broadcasting. By the way, I mean broadcasters want to know what area they're covering, and if you do coverage maps with this program, you will see that as you increase the power, the coverage obviously increases. Again, the signals are going are decreasing more or less linearly with distance. So that is for skywave signals. So if you increase your power, it will increase the radius of coverage, but not by necessarily a very predictable amount. Sometimes it's surprising how little extra coverage you get from doubling your power.
By the way, I always remind Roger that 100 watts is QRP.
It is, yeah. By the way, one of the other things this program can do up here in the upper right corner, I don't know if you can see that or if it's covered up by my ugly face, but up here in this corner, uh, upper right hand corner, you can put in different power levels. You can put in different modes. One of the things that's very dramatic is if you put F8 FT8 in here, you will find that the coverage is increased drastically. more so than going to a kilowatt with sideband. So the mode is very much a factor. The amount of power you're running, the antenna gain, all those things come into the picture as to how strong your signal will be when you get to the other end.
Which ties directly to bandwidth. CW and FT8 being very narrow can go
Exactly.
with less
Yep.
signal.
Yep. The narrower the signal, the more the software can filter out the noise, because there's in the bandwidth, the amount of noise in the bandwidth, and the bigger the bandwidth, the more noise. You can filter out the noise, and that brings the signal to noise ratio up to where your signal is copyable, even though it's no stronger than it was. It just has a better signal to noise ratio.
Question?
Yeah, which as a DXer means if somebody's gone from CW to phone and they were hard to hear in CW, go grab a cup of coffee.
Yeah, right.
Here?
Good advice.
A little bit. Question? Can you hear me?
Yeah.
Right at the beginning of your talk, you talked about 3D versus 2D signal spreading, and you said that from the transmitter up to the ionosphere is 3D, and then everything after that is 2D. I'm having trouble understanding why it works that way. Can you maybe
Okay.
explain it in more detail?
Yeah. Okay. So when you transmit, your signal is all on the ground, right? I mean, it's 60 feet above the ground, we hope, and it goes out. It spreads in both height and in azimuth until it reaches the ionosphere. So that's a 3D spreading. It's at both height and width. Once you reach the ionosphere and it gets reflected back down, then it can't go any higher. So all the energy that would have gone higher is reflected back down and joins the energy that was going directly along. And so, okay, it does it in bumps, in steps. But once you and this way of thinking really only applies to long paths where you're making multiple reflections off the ionosphere. But once you're trapped between the ionosphere and the Earth, then the rate at which your power decreases is not the same as it is when your signal is filling up the space up to the ionosphere. Does that make sense?
I don't
Maybe not.
no, I don't get why it would be, unless the fact that the ionosphere and the Earth are both curved. Well, actually, one would focus it, and the other would spread it out. So I'm still having trouble understanding why it would work the way you're saying.
Yeah. Well, you can think of it as a waveguide. This really only applies for very low frequencies in the true waveguide mode, but you can think of it as a signal being trapped between two conducting plates. Forget about the spherical part for now. Just think about the about two flat plates, and if you're sending energy, transmitting energy between, it's confined between those two flat plates, it limits the degree to which it can spread in that third dimension.
Now I got it. Yeah, it's like a waveguide, like you said.
Yeah,
Thanks for
it's
straightening
like
me
a
out
half
on
a
that.
wave. It's like a waveguide that's missing two sides.
Now I understand it. Thank you.
Okay, sorry, I didn't make that more clear.
How good it will be if the Earth was flat.
How easy. The Flat Earth Society, yeah.
One more comment. I've also been able to watch when I was tracing a particular entity, the transition between short path and long path. There's a period of time, it was about 20 minutes, where both would become a little more garbled and weaker, and then one would give up in favor of the other. So,
Yeah.
okay, at that point, it was okay, it's time to switch paths, and
Exactly.
able to get all the spots I wanted.
Looking at some paths between the eastern U.S. and Australia, I found that there were often cases where both, and I did operate from Darwin, by the way, for a while, as well as from Western Australia in another location. And I found that there are often times when both the long and the short path were roughly equal, and having the ability to switch quickly back and forth. Of course, the guy on the other end needs to switch as well to get the maximum benefit from that. Because if he's beaming long path and you're beaming short path, that's not as optimum as you're both, you know, coordinating with each other.
Or you hear the DX twice with a slight offset in time.
Yeah,
Just a
I
path,
tell you,
that's the path travel time.
another time you can hear that. I've heard this frequently on powerful shortwave stations. If you're located, say, 500 miles from a shortwave station and you're in their skip zone, but you hear them going all the way around the world, you'll, even though you're in your skip zone, you'll hear some direct signal, and then you'll hear 1/7 of a second later, you'll hear them again, and that indicates that they're making it all the way around the Earth, which is 1/7 of a second, and giving you that very distinct echo. If you're not in their skip zone, the main signal will be so loud you'll never hear the echo. But if you're in the skip zone or close to the skip zone, you know, you don't hear the direct signal very strong, but you hear the echo quite strong, and it becomes quite pronounced.
But
Let me
John, as I
Yeah.
mentioned to you, I worked in broadcasting also. My highest power AM transmitter was 50 kilowatts, which I assume is QRP compared to the power you worked with.
Yeah, on shortwave broadcasting, it had become pretty standard to use 500 kilowatts, and a lot of the Chinese stations are still doing that. We did that in Ecuador, and we also had an antenna gain of 22 dB, so the ERP was fairly strong. And by the way, my ham shack was located only a quarter of a mile from that antenna in its main beam at certain times. That made it very interesting from a front end overload standpoint.
Other questions?
I'd just like to comment that this is one of the best talks I've heard in a long time, and hasn't been. I haven't heard the same information from 10 other sources. I really wanted to thank you and congratulate you on new knowledge we haven't heard 100 times. Here, here.
Well, thank you very much. I appreciate it, and I've enjoyed it.
Anything else? Any other questions?
I'm trying to figure out your accent. It sounds like Virginia to Kentucky to me. Where are you from?
East Tennessee.
Okay, not far off then.
Yeah.
Okay. Thank you, John. Great talk. We're really glad to have you. And if you haven't read his article in QST, February QST, as I recall, or was it January? March? Okay.
March.
This month's
And let me just say there was a couple of typos in that related to how to calculate the distance around that takes energy to get to from north to south pole. Ignore the math errors and just the conclusion that the final answer was correct. That was
well, I did read the article, and that's how I found you.